today. So, in this lecture we are going to discuss the various protection and restoration mechanisms which are usually employed in optical networks. So, we will be talking about protection and restoration. Now, of course, we have to discuss what is protection and restoration, why we need them, what is protection, what is restoration, comparison between the two, and the different schemes of protection. So, this would be our general outline of presentation. Now, network is unreliable somehow. Okay, I mean, so many failures can occur. A node may fail, a link may fail, a link may get cut, some fiber optic line may get cut in between because somebody cut it while digging a hole or something, or a node might fail. There may be power failure at nodes and so many things. So, there are failures in the network, but if you remember that one of the most important places where we deploy optical networks is in the core of the network, and the core of the network connects so many people to so many other people and it is so very vital that we cannot allow the services to be severely disrupted, because that would have a very grave consequences. And anyway, these service providers attempt to give a very high level of service. So, although failures are unavoidable in real life, we have to find some way of combating this. That means, if there is a failure, we want to recover from it as soon or as fast as possible. So, that is what protection and restoration is all about. And another thing, that when we want to give some reliability, protection, restoration, etc., we always, in some form or other, we always have to bring in some redundancy. Okay. Without any redundancy, a system cannot be protected, it cannot be restored without any replacement, etc. So, there has to be some redundant capacity in some form in the network in order to achieve protection and restoration. So, how this is done, that is what we will discuss. Now, protection and restoration are the mechanism to recover from network failure. Their difference will be discussed in the following parts. So, why we need protection and restoration is now clear: to recover from network failure, to prevent a lot of data loss. Now, that is another point. What do we mean by prevent a lot of data loss? Is it that some data is lost? The point is that I mean, here we will be talking about protection at the say in the optical level, or the low in the transport level, that is the low physical level. All right. Now, above this physical layer, if you remember, there are a whole lot of other layers like data link layer, network layer, transport layer, etc., and they may have their own protection mechanism. So, what they might do is that they might be able to tolerate, in some cases, if such a protection is sort of implemented at a higher level, such protection usually would tolerate a small amount of data loss, which they will maybe they will retransmit or do something in the protocol to take care of that, and we will be talking about these later on. So, that means, so within that limit, so we do not have a 100% I mean tight case, so we have something to play with. So, within that limit, if the physical layer can come back up, then that is nice. Then the end user who is sitting, of course, at the top of the application layer, he would not notice anything, that he would not notice that a failure has actually occurred. So, this is our general goal. And of course, to prevent a lot of data loss and to provide reliable communication service. So, this is the reason for having protection and restoration. Protection is the primary mechanism. This is fast, and routes are usually pre-planned. We will come to this part later on. Whereas restoration is a secondary mechanism used to provide more efficient routes or additional resilience, etc., over and above protection. So, we will see them, both of these. Now, for techniques of protection, we could protect a path, which is called path protection. We could protect a link, that is called link protection. There are various schemes of protection like 1+1 protection, 1:1 protection, 1:n protection, m:(n) protection. This all depends on what kind of redundancy we have built into the network. So, we will look at some of these techniques one by one. So, what are the considerations and trade-offs that we have for protection? We want support for fast protection, and time is dictated by the client layer. This is what I was talking about earlier, that in the client layer. So, whatever the higher layers, so we are talking we are clubbing all of them together and calling them client layer, let us say. And in the client layer, we may have some resilience, that means some small amount of data loss maybe we can tolerate. Okay. So, depending on that, so and beyond that, of course, it will fail, the service will fail, I mean it will be taken that the service has failed. So, that is dictated by the client layer. So, that is the constraint within which we try to do our protection and restoration at the bottom layer, that is the physical layer. Then of course, we require some switching technologies, as we will see, and how to implement protection. It could be through dedicated hardware or through software. Here we will only be talking about, since we are talking about the physical layer. So, here we would mostly be concerned with hardware protection, where some extra hardware has been put in order to take care of this protection. Support for low priority traffic, that is another consideration we might have. So, low priority traffic supported using the protection bandwidth, traffic dropped in case of a failure. As I mentioned earlier, that in order to give some protection capability into the network, we have to build in some kind of redundancy over there. Now, when there is no failure, naturally that redundant link would be idle, or if it is a link or if it is some other, anyway there will be some redundant provision in the network, and that redundant provision is going to be idle. So, what you could do is that if you have some low priority traffic which could be dropped whenever there is a problem. So, what you can do is, under normal circumstances, you can use your extra provision in the network to carry the low priority traffic, and as soon as there is a failure, naturally this extra provision is going to be used up for providing protection, restoration, etc. So, the low priority traffic would be discontinued. So, that is one thing we could do. Support for mesh topologies. Mesh topologies are bandwidth efficient. So, fast signaling mechanism, flexibility in choice of routes, pre-planned routes, etc. So, support for mesh topologies, if we have, so that is also nice. As a matter of fact, if you remember our discussion about different types of topology, we have star, tree, ring, mesh, etc. These are the different possible topologies. Out of this, and of course, we have a simple point-to-point connection. Now, out of all this, point-to-point connection, ring and mesh, these are the three topologies which dominate most of the WAN. All right. Traditionally, first of course, when you want to communicate between 2 points, first you set up a point-to-point link. Now, if you consider that link to be quite important, etc., then what you would like to do is that you would like to put in some kind of reliability over there through, maybe by making it into a ring. For example, we discussed SONET, and SONET gear quite often they are put in the forms of rings, and rings which touch. Okay, so mutually touching rings. So, for example, the telecom people, they put up all these SONET rings through fiber optic networks, and rings are quite easy to handle, and we will discuss the protection mechanism in ring quite a lot. But if you go to a wider geographical area, a ring may not be possible, or it may not be feasible due to various reasons. So, what you have is a mesh. A mesh, if you recall, is just a it is a graph where the nodes are connected in some fashion. It is a connected, it has to be a connected graph, and actually later on we will see that for giving proper protection, not only it has to be a connected graph, it has to be a bi-connected graph. That means between two nodes which are communicating, there has to be two alternative paths which are linked disjoint somehow. Okay. Otherwise, we will not be able to give protection. But anyway, so giving protection in mesh network, so that is also an important consideration. Other important considerations are maintenance of a large distributed routing tables, that is pre-computed routes or up to date topology maps. So, you have to maintain this dynamically, because because a network is a very dynamic thing, as links come up or go down, or nodes come up or go down, this may have to be recomputed and stored in a distributed fashion. And then of course, we would like to have support for all failure mode, node failure, mesh networks, for mesh networks, for ring networks, or it may be of course link failures. Okay. So, first let us talk about path protection. It uses more than one path to guarantee the data be sent successfully. So, if you look at this graph, so we have a 6 node graph where 1 and 6 are communicating, and on the top through the dashed line we show the primary path, which is the primary connection between 1 and 6. Now, what might happen is that the link between 2 and 3 might snap due to some reason. So, we have already got a backup route which is calculated through going through 1, 4, 5 and 6. So, we will channel our communication through the backup link, and please note that this backup or secondary path from the source to the destination is link disjoint. That means that does not share any link with the primary path. So, that is a requirement. So, that if any link in the primary path fails, I mean assuming only one failure, which means that the backup link is all intact, and you can switch to the backup path for this particular communication. Now, path protection, there are various ways to protect a path. That means various ways, these various ways means that the various ways of provisioning the extra bandwidth or capacity in the network, so that you can give protection. As I said, that you need to give some redundant, you need to build in some kind of redundancy in the network. So, there are various ways you can build in this redundancy, and the schemes may be divided as dedicated path protection or shared path protection, and dedicated path protection may be shown as 1+1 protection, or shared path 1:1 or 1:n protection. So, we will look at these one by one. So, this is an example of 1+1 protection. So, you have the source on the left, and then you have the destination on the right. So, it is communicating. What you can see is that this from the source, it is the signal is coming to a splitter. If you remember that the splitter is going to split it into two halves, maybe of maybe equal power or something, and then the same signal is being carried through two different links. So, and over here there is a switch. So, what this switch is, it determines which signal is better and maybe switches to that, and communication is going on. If that particular link, say this one, the top one fails, it automatically switches to the other protection link. So, this is kind of some kind of hot redundancy which we have. That means it is on, both the things are on. There is a redundant source of information at the in the destination side. So, if the primary one fails, the secondary one is already on. Okay. So, this is all very good. So, protection would be very fast. Only trouble is that for each such path, you will have to give an alternate path which is also being used at the same time. All right. So, this is a dedicated path protection. For this particular path, there is a dedicated alternative path. Okay. So, that is why although this is very good, but this is costly. Okay. Now, we come to shared mode protection. So, in the shared mode, the figure looks almost the same, except if you note that this splitter on the left has been replaced by a switch. So, what we have is we have a working fiber and we have a protection fiber. So, unlike the 1+1 protection, this is not a hot standby, this is cold, in the sense that the protection fiber to start with is not carrying any signal, let us say. So, the source it is just simply passing through the switch, signal from the source is passing through the switch, then down the path through the destination switch to the final destination, that is what is happening. If the working fiber goes down, then this switch as well as this switch will flip and the protection fiber would be in its place. So, why is it shared? Well, if it is only the point is that this protection fiber, since this is not a hot standby, meaning that since this is not carrying any signal under normal circumstances. So, under normal circumstances you could share this path with something else, okay. I mean, you can use this to send some other channel or some other information, etc. So, that is why this is a shared mode of protection, and generalizing this excuse me, generalizing this, we get the 1:n protection, where n lines is sharing one protection line, one protection line for protection. So, these are the n lines from 1 to n. So, we have the inputs from 1 to n, these are the n sources, and let us say so many destinations. So, they are going to 1 is maybe going to 1 dash, 2 to 2 dash, and n to n dash, and so on. So, this is the normal mode of operation. This part of the network is for normal mode of operation, and each of them are connected to a switch over here. Another link from the switch comes to one bigger switch. So, this is an n input port over here, and then there is a single link from this switch to this switch and the destination side, which again feeds to all the switches. So, what would happen is that in case there is a failure in any one, let us say ith link from 1 to n, out of that the ith source to ith destination, it is going through the, let us say, the ith link, and the ith link fails. So, what this ith switch could do is that ith switch could switch the signal from the ith source to this particular switch at the bottom, and now the protection fiber would be carrying that ith that whatever signal was flowing down the ith channel over there, and then it will again feed it to the ith switch on that side. Of course, these two switches have to communicate that the ith one has failed over here. So, you switch it to your ith mode, or this switch may sense it that this line has gone down. So, it will take the signal from this line. So, this is one protection fiber is being shared by these n working fibers, okay. And as I mentioned earlier, that when everything is fine, this protection fiber could be carrying some low priority data. So, when there is everything is fine, so these n working fibers are actually carrying the most of the important all the important traffic. So, some low priority data could be flowing down the protection fiber. As soon as there is any failure anywhere, the low priority data would be stopped or it will be dropped, and then this protection fiber would switch to give the services between the nodes who has experienced a link failure. So, just as we have path protection, that means for a path you try to give an alternate path. Similarly, you could do it at the link level also. As a matter of fact, that is in general it may be more efficient or more proper to do that, because if you have n nodes, potentially, and if n is slightly large, potentially you have a very large number of paths through the network, and for each path having an alternate path may not always be a very good idea. So, we concentrate at the link level, and for each link level we may give an protection. So, use an alternate path if the link has failed, okay. So, this is the, once again this is the primary where the link may have failed. So, I have an alternate path to that from 2 to 3, 2 to 4, 4 to 5, 5 to 3. This alternative, please note, is for the link from 2 to 3. Okay, we will have another, I have another diagram for that. So, dedicated link protection is not always practical, although sometimes you may have it. Shared link protection is practical and it is quite often implemented, and it may fail when in of course, this link protection may fail because here you are only provisioning for the failure of a link, but if a node fails, then it may lead to some complication, as you will see. So, to compare between path switching and line switching, path switching of course is a coarser scheme and line switching is a finer scheme, and line switching can again be a span protection. A span would may be several links together, that may be a span or a line protection. In mesh networks, of course, restoration is possible only if the graph is two edge connected, that is bi-connected, which means that there are two edge disjoint paths between any pair of nodes, so that no single edge failure can disconnect the network. So, this is a necessity, and we usually try to keep it that way unless it is very difficult or very it is not cost effective, etc. Now, protection in a mesh network is of course more complicated than a ring. Simple minded scheme would be two edge or node disjoint paths for each connection, 1 plus 1. As is mentioned here, this is not very efficient. There may be many paths, and provisioning a double the number of paths which are pairwise mutually node or edge disjoint, that may be very difficult. That may be a lot of extra provisioning in the network. A better approach would be line protection, which of course has a problem of coordination. I will show that later on, or protection cycles in meshnet. Again, I will show this. Now, in the path layer and the mesh protection of mesh networks, so protect mesh as a single unit. Pre-computed routes, that means all the possible routes and alternative routes are pre-computed, 1 plus 1 path protection, protection route per light path or protection route per failure. We will discuss this later, but as I said that this is a costly alternative. Or what we might do is that on the fly route computation, that means it is not pre-computed. As there is a failure, centralized route computation and coordination at end nodes, or distributed route combination. So, all these are possibilities. So, this is an example of a mesh network where let us say this is the primary path, this is the alternate path. This alternate path may be pre-computed or it may be computed on the fly when there is a failure. Similarly, from here to here, this may be the primary path and this is an alternate path. Okay. Please note that this communication as well as this communication, both of them are going through the same fiber. So, maybe they are going through a different through different wavelengths, or maybe they are combined together. So, there are various ways of handling this. So, let us look at some diagrams once again. Say this is the this is a network, mesh network, naturally, once again the same 6 node network, and this is the normal operation, that is the communication from this node, node 1 to node 6. Now, there is a link failure over here. What you might do is that you might switch the entire path like this. So, this was the pre-computed path for this path. So, you switch to that. This is one possibility. Or this particular span, the span could be like from here to here or from here to here, that may have an alternative path. So, through which you to which you switch. Or this particular line may have this alternative, that means say from this node to this node, if this is the link, the alternative to this link is this section from here to here to here to here. So, as this thing, it is trying to go through the same path, but then it takes a diversion when there is a link failure through the alternative which is provided for this particular link. Of course, here I have shown only one node coming into this, but this path may be, you can appreciate that this path may be very long. So, you do not have to recompute the path over the entire length, rather locally you can recompute that for this particular link what is the alternative. So, the alternative may well be through some local nodes only. So, this path is just gets a slight diversion, that is line protection. We talked about protection cycles in a mesh network. Now, for protection cycles what we do is that for each of the paths what we try to form a cycle, all right, cycle of provisioning of light paths, let us say. So, the point in the cycle is that if suppose you are going through some arc of the cycle and if some link in between breaks, you can always go the in the other direction, all right. So, you try to form these cycles in the mesh which you keep ready and pre-computed, so that whenever there is a failure you can switch. So, you can see here, so there are pairs of fibers going in the both the directions, and there are you can form cycles over there. One of them is a protection, would be a protection edge, maybe the inner one, and one of them would be the working edge, and if one of them fails the other would automatically take over, in the other direction will automatically take over. So, this is another example of a network with both working and protection fibers. The working fibers have been shown in solid lines, whereas the protection fibers have been shown with the dashed lines. So, of course, maybe once again you must realize that you may not provide the same level of protection to all paths or to all parts of the network, depending on which part you consider more sensitive or more important, you may put your protection there. So, a network may be, or a mesh network may be partially protected, some of the paths may be protected, some of the paths may not be protected. So, some more cases, line protection in a mesh network. So, what we have is a unidirectional light path from node A to node D. So, from node A to node D we have an unidirectional light path going maybe like this, all right, through nodes B, C and E, sorry. So, A to D, so we are talking about this path, A to B to C and then to E. Now, after link BC, let us say, fails, so this link BC fails, light path is rerouted by nodes B and C along the route A, B, F, E, C, E, D, A, B, F, E, C, well, F, E, C, D, C, oh, okay, A, B, C, oh, sorry, the unidirectional light path was going from A, B, C, E and then to D. So, this was the path A, B, C, E, D. Now, BC has failed. So, A, B, F, E, C, E, D. So, you can see what has happened. There was no point in coming from E to C and then back from C to E. Okay, this really looks stupid. What has happened was that we were doing a line protection. That means, for BC my protection was from B to F to E to C, because I want to go from B to C. So, I am going from B to F to E to C. So, now BC has failed. So, that is what I do, and from that point I continue wherever I was going, and actually I was going from C to E to D. So, once again from C I go back to E and then to D. Okay. Such a thing is possible. Please note that such a thing is possible because we are taking a local decision. Local decision, that means for this particular link what to do in the case of a failure that has already been pre-computed. So, we are not taking a global picture. If you had taken a global picture, of course, here I have shown you a very small graph. So, you can immediately see the entire global picture with your own eyes, but for local nodes may not have the global picture that where this node is coming from and where this node where this path is finally going to. So, all the intermediate nodes may not have the global picture, because if all of them had the global picture, maybe they could have computed a better path, but this is what it is for line protection. Now, line protection in a mesh network, and here what might happen is that erroneous connection due to failure of a node being treated by its adjacent nodes as link failure. Now, this is one case of the so called race condition might happen. What might happen is that say node 1 has failed, okay, node 1 has failed. So, what would 6 do is that 6 should may assume that the link from 6 to 1 has failed. So, whereas 2 may assume that the link has from 2 to 1 has failed. So, both of them perceive as two different failures. So, they take some local decisions, and it might lead to some funny situations where you are going in a cycle maybe, or other kinds of things may happen. After node 1 fails, node 5 gets connected to node 4 after node 6 and 2 invoke line protection independently, alright. So, if they take the if they perceive the same failure, the actual failure was of that of node 1, but if they have perceived it differently as failure of link 6.1 and the failure of link 2.1, and they have taken independent action, that may lead to race conditions. Now, the advantages of disadvantages of protection, because we will also be talking a little bit about restoration. Protection of course is simple, it is quick, do not require much extra process time, and this is the important part, that since this is quick, so as I mentioned earlier, that there will not be a lot of data loss, okay, there will not be a lot of data loss. Actually, for example, a sonnet ring would sort of come back up from a failure in less than 50 milliseconds. So, that is a benchmark. So, in less than 50 milliseconds you are back in action. So, whatever little you might have lost in the during that time, that would be taken care of by the higher layer protocols. So, but usually they can only recover from single link faults. If there are multiple link faults, then all kinds of funny things may happen. Inefficient, of course, it is inefficient usage of resources, because protection needs a lot more lot of resource, okay, even if you are sharing them, and of course dedicated protection needs even more resources. Restoration. Well, we can once again we talk about path restoration and link restoration. What we do is that we compute the path after the failure, and the resource is reserved and then used. So, in restoration what you try to do is that you try to look at the current actual situation. So, you try to have some protocol for keeping track of the present situation, and then you compute some route, then you reserve the path, and then you restore the original service. So, this is got some software part, so some data has to be processed, etc. So, this usually takes more time. So, this has a hardware as well as a software aspect to it. The path is discovered at the end nodes of the failed link. So, this may be more practical than path restoration, because path restoration, so you have both path restoration and link restoration. Path restoration means the path may be long, and to find out an alternative may be more difficult, whereas links are between adjacent nodes. So, they may quickly find an alternative. Advantages and disadvantages of restoration are the following. Usually can recover from multiplex element faults, because you are sort of having some protocol to exchange information and then find the current situation and then form the alternative, etc. It is more efficient usage of resources, it is more complex, it is slower, it requires extra process time to set up path or reserve resources. So, for comparison between protection and restoration, protection the resources are reserved before the failure, they may not be used. Restoration the resources are reserved and used after the failure. So, this is the main difference between the two. Route, in protection it is predetermined, restoration can be dynamically computed. Resource efficiency protection naturally is low and restoration is comparatively higher. Time used for protection is short, for restoration it is longer. And reliability, protection mainly for single fault, whereas restoration can survive under multiple faults? Well, it is not that it will always survive under multiple faults, it depends on where the faults are, but if it is survivable after the multiple points, if you take a global view and see that okay, still I can give the services, so restoration will take care of that, whereas protection, for protection it may not be possible to handle multiple faults. Implementation for protection is simple and restoration is naturally more complex. For optical networks, of course, we not only talk about physical links, we talk about virtual wavelength paths or light paths also. Routing can be centrally controlled or distributed, resource reservation, forward reservation as well as backward reservation, as we do in optical networks. We will talk about this a bit more later. Now, let us come to this all important topic of fault management in ring networks. As I said that ring networks are very ubiquitous in WAN. Okay. All the telco people love these rings because naturally it can give allows them to give a very high level of service. So, we have so many rings, these sonnet rings are very common. So, and rings are a very common kind of topology, and one of the chief attraction of the ring topology is its capability to allow some kind of protection and restoration with some redundancy inbuilt, as we will see. So, we will look at two different cases, unidirectional path switched rings and bidirectional line switched rings. So, UPSR and BLSR. So, this is a diagram for UPSR. So, we have AB means A to B and BA means B to A. First of all, you see that we have these two rings. So, we have this working fiber as well as a protection fiber. Working fiber is going in only one direction and protection fiber is going in the other direction, in the counterclockwise direction. So, for connection from A to B and from B to A, so A to B, this is A and this is B, and my working fiber, so I can go my working fiber is going in this direction. So, A to B is really going in this direction, B to A is coming in this direction. So, A to B, B to A. So, this is the this is the protection fiber part. So, A to B, the working fiber is going in the other direction. So, A to B is going like this and B to A is coming all the way like this. Let us say if the outer one is the working fiber, it is through the outer ring. So, A to B, this is the path, and B to A, this is the path. Whereas, for protection purpose, and this is please note that this is a 1+1 scheme. That means, for this the alternative is already provisioned and maybe something like a hot standby. So, A to B, that is through the protection fiber, and A to B is now this path from A to B is going via D and C. So, A, D, C, B, that is A to B, and B to A, the protection path is from this through the protection fiber. So, if there is a failure anywhere, this can still continue. So, this is a unidirectional path switched ring. So, there are some limitations of UPSR. It does not spatially reuse the fiber capacity. So, what is happening is that since this is unidirectional, what is happening is that even if two nodes are side by side, but if they are in the wrong direction, then it has to come all the way through. And naturally, all those links, even if you are talking about particular lambdas, I mean a WDM system, if it is not a WDM system, then the ring is entirely sort of covered by this. Otherwise, even if you are talking about a WDM system, what is happening is that at least one lambda around the whole ring for all the links in the ring, and they are getting occupied because two side by side things are wanted to communicate. So, it does not spatially reuse fiber capacity, and if some side if there is some you could use it for some other purpose, that is not possible in unidirectional rings. Each bidirectional sonnet SDH connection uses up capacity on every link. So, that is the this thing. You see, from if you look at the previous picture, we are just talking about a connection from A to B and B to A, that is all. So, this entire ring now has been used up, assuming only one wavelength, the entire ring now has been used up. These ADMs of course are the ADMs of SONET. So, it is efficient for lower speed access networks, one to multi-point only, alright. And the other problem which may become a problem is that delays are different for the two paths, because one of them is small and the other one is quite large all the way around the link. So, the delays in the two paths are quite different. Remedy could be bidirectional lines, that means bidirectional line switch rings, BLSR. So, we were in UPSR, now we will be talking about BLSR, bidirectional line switch rings. This provides spatial reuse capabilities and additional protection mechanisms and adapts span as well as line protection. So, we will have a look at both of these. So, this is a 4 fiber bidirectional line switch rings. So, once again we have two working fibers on the say the outer two ones and two protection fibers, the inner ones. So, we have actually 4 fibers. Okay. So, this is a 4 fiber system and it is going. So, two of them. So, we are using two such working fibers. So, one of them is going in one direction, the other is going in the other direction. So, this is bidirectional, we can communicate both ways. So, if A to B and B to A both can communicate on the working fiber in this part at all. So, the rest of the space can be used for other communication. So, spatial reuse is much better for bidirectional line switch rings. And the protection fibers are there, because if there is one of them fails, then the protection fiber may take up. This is a span protection. So, we are talking about say bidirectional traffic supports maybe 16 nodes or some distance, etc. So, from A to B, a span, for a particular span you may pre-compute that if this span goes down, what is the alternative span. This one is a case of line protection. So, if this line fails, what is the alternative line? Now, the alternative line of course may go in the other direction in other direction depending on what the failure is. So, there are many different possibilities with this BLSR. There is also a 2 fiber version of BLSR, namely BLSR 2. So, here both the fibers are working as well as protection fiber. That means, if one of them fails, the other one will give the protection in the other direction of the ring. Okay. If you note that the rings are going in the in the opposite direction. So, if there is a line failure, so both of them these are working as well as protection fiber. That means, A to B is communicating in this direction, B to A is communicating in this direction, but if one of them fails, the other one, so the other one will give the protection by going in the other direction. So, in that case, in the case of a failure, you have to go all the way round. Then of course, you will have to reserve that resource, and if there is something already going on here, you may be blocked or this may have to be dropped and so on. So, all these are there. Naturally, you have 2 fibers, so you have less flexibility. So, but with 2 fibers also we can get this bidirectional thing going. So, comparison of different types of self. So, these are all self healing rings. What do we mean by self healing? What happens is that the nodes that the nodes, these ADMs and these SONET gears, etc., they are programmed in such a fashion, so that as soon as they sense a failure, they know what local action to take and how to adjust the switch internally, so that it is automatically switches from the working fiber from the working span or working fiber or whatever to the protection side. Okay. So, that is why these are self healing rings. So, they heal automatically, and as I said, these SONET rings really do this in less than 50 milliseconds, the entire thing will again be up. So, there are, we can compare the 3 UPSR, BLSR 4 and BLSR 2. for example, fiber pairs 1, 2 and 1, transmission receiver pairs are 2, 4 and 2. Spatial use in UPSR it is none, in BLSR it is there, and in BLSR 4, 2 it is there. Protection capacity is the working capacity is equal to the working capacity. Link failure is path protection in the case of UPSR, or span or line protection in the case of BLSR 4. In case of BLSR 2 it is only line protection because it will have to go in the other direction. Node failure is path protection, line protection and line protection. Restoration is faster in UPSR, somewhat slower in BLSRs, and speed is low, high, restoration speed is this, and node complexity is low, high and high. Anyway, another thing we talked about is the dual homing. Okay. By dual homing we mean that suppose there is a you want to deploy your network in such a way that it is very mission critical and no failure, so we want a hot standby. So what you might do is that you may get connected through two different hubs, and so you may so what you want to do is that you want to dual home to these two hubs, and these two hubs take independent path to your destination. So that is possible. So this is this shows dual homing to handle hub or node failure. So we have these 4 ADMs, once again 4 nodes, let us say A, B, C, D. So the end node, let us say the end node is A, and these are the two hubs B and C. What we want is that not only some link failure, but even if one of the hubs fail, I should still be able to communicate. So what you do is, on this ring you communicate with the hub 1, let us say you are communicating with hub 1 through this A, D, C, B, and you are communicating with hub 2 through A, B, C. Okay. As you will note that even if one of the hubs fail, the other one you can still communicate through the other one. So this is another kind of protection. And finally, this point I have mentioned before, just a reminder that a network consists of many layers, and each layer may have its own protection mechanism built in, independent of other layers. So there are both advantages and disadvantages to this. Okay, advantages we have already talked about. So this is an example of a WDM link carrying SONET traffic. So there is a WDM link. So there is SONET ADM, this is a working fiber pair and protection fiber pair, and please note that the pair has been shown as one line over here, because usually as you know that fiber optic line is a simplex, is a simplex line. That means it goes in only one direction, and there is a source in one side and the detector on the other side. So usually these fibers always come in pairs. Okay. So the other side is for the communication in the other direction. So we have a working fiber pair over there and a protection fiber pair through these WDM links. Now at and look at this 1:2 protected scheme. What is happening is that there is one protection fiber pair, there may be one protection fiber pair, and through the working fiber there may be multiple links going, multiple virtual links going through the working fiber using different wavelengths. Okay. Normal operation, A is the normal operation, and B link is cut and the traffic is restored by the optical layer. That means you automatically assign new wavelengths or new paths through the fiber, etc., to bring it up. So this you may do at the optical layer rather than at the electronic layer. But protection, a SONET ring, SONET. So actually what is happening, the case we are talking about here is that SONET is riding on the optical layer. So you have the optical layer at the bottom, then you have a SONET on top of it, and of course on top of SONET also there will be the data link layer and then so on, all the other links. What we are saying is that each layer may have its own protection mechanism. So, for example, and I mentioned this, that the sonnet will also have a protection mechanism of its own. So, if a sonnet LTE that is the sonnet line terminal equipment, if it senses that the next that it cannot communicate to the next LTE, this will automatically reroute the traffic and try to reroute the traffic in the other direction. And sometimes this is good to have multiple protections at multiple layers, but what might also happen is that they might sort of either cancel each other or they might go into a race condition. So, these are the disadvantages of having protection at various layers. This could, so there could be some disadvantage also if they are not very well coordinated, which usually would not be, because these layers are sort of independent of each other. So, they talk only to their peers and go through their own protocol and give the protection. Apart from this, of course, the other disadvantage is that you may redo some part of the protection unnecessarily when you are doing it. So, you may be unnecessarily duplicating the work at various places. So, that so these are the disadvantages of having protection at multiple layers. So, advantage, what is the advantage of optical layer protection? Speed and efficiency, and limitation would be detection of all faults may not be possible. Protects traffic in units of light paths. Okay. So, this is another problem. As I mentioned, that light path, the granularity is very coarse. Okay, it may be 2.5 Gbps. So, you are really giving protection at that level of granularity, which may be quite high. And as I just now mentioned, that race conditions, when optical and client layer both try to protect against the same failure. So, and of course, on the optical layer you have some more I mean one more dimension to play with, which is in case of a WDM, that means you have the different wavelengths. So, you can have, instead of 1+1 link, you can talk about 1+1 wavelength path selection. So, you can sort of try to select two independent light paths, and signal is based on both protection and working fiber. If you are doing 1+1 protection kind of thing, receiver chooses the better signal. In case of a failure, the destination switches to the operational link, that is the operational light path. Revertive or non-revertive switching, that means if the original link comes back, it may revert or it may not revert, and no signaling is required. So, that is the unidirectional light path. So, I mean I have just shown you some of the schemes which are used for protection and restoration, and as I mentioned that the schemes may be partially deployed and some of the parts may be protected, some of the parts may not be protected, and so on. But the essential idea is the same, that you build in some kind of redundancy. That redundancy may be in the form of entire fibers, or the redundancy may be in the form of light paths or wavelengths. It may be pre-computed and pre-reserved like 1+1. It may be pre-computed but not pre-reserved, so like in a shared one, or it may be computed as and when the failure occurs, that is in the case of a restoration. So, there are various approaches to it. So, depending on how critical the problem is or how critical the application is, what is the cost and how much extra provisioning you can do, you can choose your own way of protection and restoration. Thank you. Good day. So, today we will talk about multiple access. Okay. Now, what is multiple access? If you remember that we had 7 layers in the so called OSI stack, the top one being application, then we have presentation, session, transport, network, link and physical. Okay. We had been mostly talking about the physical layer till now. although for optical networks we sort of ventured into some of the higher layers, but from this lecture onwards we want to concentrate on the link layer. Okay. Now, what medium access does is it coordinates competing requests. Requests for what? For medium. That means that there is a medium which may be an object of contention, meaning that I mean several nodes may want to use it, and this medium access control protocol has to do with how to handle that. So, sharing of link and transport of data over the link, that is the in general the description of what the data link layer does. So, when we share a link, there is a question of competing requests, and we have to have some way of resolving that. And of course, there is also a question of transport of data over a link. A link, if you remember, when we say a link, I mean that two nodes which are connected, the nodes may be computers or routers, switches, etc. The two networking nodes, they are directly connected. Now, when I do like this, it might mean a cable, a copper cable or a fiber, or it might mean a shared medium like the free space. Okay. So, there is but there is some way of communicating directly between these two nodes. That is what we mean by link. That means that is just one hop in the network. That is what we are talking about in the data link layer. So, there is a question of reliable transfer of data over this link, and if this link, like when you have a free space transmission with so many nodes in the network, now so many people would like to transmit. So, there is a question of sharing this medium, and there is a question of who would access it when, and just as a free space could be a shared medium, similarly if you remember that if you have some kind of a bus, if you remember our discussion about topology of networks, when we have some kind of a bus from which a number of nodes are hanging, and that bus may also be an object of contention. So, that bus is the medium through which communication is taking place, and there is some kind of competition or sharing between this medium between the nodes. So, we have to handle that. That is the other thing. So, examples of contention based are Aloha and slotted Aloha. These refers to some protocols which are used in satellite communication. So, we will discuss these when we talk about satellite communication. We have CSMA, it stands for Carrier Sense Multiple Access, or CSMA CD, which is Carrier Sense Multiple Access with collision detection. There are other variants of these like Carrier Sense Multiple Access with collision avoidance and things like that. So, this Aloha, slotted Aloha for satellite, CSMA, CSMA CD or specifically CSMA CD is used by Ethernet in many situations, and then we have our CSMA CA maybe for cellular communication, etc. So, these are contention based MAC. And round robin, these are token based protocols, and so two very common ones are token bus and token ring. So, actually we will discuss these in the next in this lecture as well as the next, we will be discussing these.